For today's lesson, we are going to continue our investigation of quantifiers and sets. And to start off, we are going to look at the following theorem that we encounter in calculus. If f is a differentiable function, then f is a continuous function. Now, the way that it's written, it is unclear what f is. It's a differentiable function, sure, but is the function, is its domain the real numbers? A subset of the real numbers? Is it a subset of 2 space or 3 space or Rn? We encounter this theorem in various settings throughout calculus. In Calc 1, we are always restricted to one variable, and so our domain is always a subset of the real numbers. That also includes the real numbers plus a possibility. But then when we look at multivariable calculus, we now are looking at functions that have 2 inputs or 3 inputs. So now we have our domain could be the plane or 3 space or subsets of them. And so when we write these theorems down, and when you encounter a theorem in a book that is written in this form, it is implicitly understood from the context of the course what the universe of discourse is. But since I randomly chose this theorem, and we have not talked about differentiable functions or functions for that matter in our course as of this moment, we do have this ambiguity. What is f? And so we can remedy that by adding a statement at the start of the theorem that says, so if we want to go ahead and restrict to cases where we have that f, and this is a notation that we introduced in linear algebra, and what it says is that the inputs are real numbers. So we have a function f whose inputs are real numbers and whose outputs are also real numbers. And so these are just the one variable functions that we see and encounter in calculus 1. And so let f from R to R be a function. And then we can go ahead and continue the statement. So once we have this, now if f is a differentiable function, then f is a continuous function. And so our discussion of universe of discourse, as our book calls it, is a reference now to this let f be from R to R. That is telling us what are the possibilities for the functions that we are considering. And so with that in mind, we can now go ahead and translate this into symbols. And so we can go ahead and say the following. So now, so I'm going to just write what I said out loud. So universe of discourse is going to be functions from R to R. So with domain R and range, actually with domain R and outputs in R. And so we now have our universe of discourse. So if we were to write this down symbolically in the language of propositions, we know that we have an if-then statement. So we can say that the if part is P implies Q. And so we have f is differentiable implies that f is continuous. But what we really are saying is that every function that is differentiable is continuous. And so we actually do have a quantifier at the front. We have for all f in our universe of discourse. If f is differentiable, then f is continuous. And so we have that hidden quantifier right there. So the next thing we want to do is let's write down the statement that each integer is either even or odd. And so how do we go about that? And so next we are going to write that each integer is either even or odd. And so how we go about writing this? Well, let us go ahead and switch our universe of discourse. So we could change our universe of discourse to be the integers, but we can also choose them to be the real numbers. The integers are a subset of the real numbers. So we can say let the universe of discourse be the real numbers or the integers. We are going to be making a statement about the integers, so it's perfectly fine to put it to be the integers, but the main thing is we will be restricting in our statement in the same way that we said f is indifferentiable. And so we want to have that every integer is even or odd, and so we can say x is an integer implies that x is odd or x is even. And so we have this here. But again, as I mentioned just now, as with our translation of the theorem, we have that hidden quantifier because we want to say this about every integer x. And so we have at the very front a for all x. But we also have the definitions of what it means to be even or odd. So we can also write this in the following way. And what I'm going to do now is just rewrite the same phrase in different ways, and they are all going to be equivalent. And so we can write this as for all x is in z implies that x is even. So we can write this as, so what does it mean to be even? That means that there is some integer n such that x is equal to 2n. So we can write over here, there exists some integer n in z such that x is equal to 2n. And so that's what it means to be even. But now in practice, when we say this out loud, we're reading this as there exists an n in the integers such that x is equal to 2n. Bellman, and also in logic, it is common to omit the such that we will say out loud in words. And so I'm going to do this for the second portion since we have a very similar setup. And so x is odd, similar, we use by definition, there exists some integer n, but instead of writing the such that, it's now implicit in how I'm writing it, where I have there exists n in z, x is equal to 2n plus 1. And I put a comma there, but we don't need to put a comma. And so now, there is nothing in between here, but when we read this out loud in English, we really are saying there exists an integer n such that x is equal to 2n plus 1. And I forgot a parentheses to close this off. And similarly here. And so now we have our statement. Now, this is a way of writing this, but we could also write this in a different way. We could, instead of writing this as an implication, as we are doing here, we can just simply say for all x in z. And so now we're saying a statement about what happens for every integer x. And now we have that this here, we will go ahead and then just rewrite this portion here. And so now I'm just going to go ahead and copy paste. And so we have this. And so these are all equivalent formulations. And so in general, if we have for all x, and so now this is now in generality, we're no longer working with the integers or real numbers, but just we have some universe of discourse, and we have some set A. And if we write for all x in A, P of x, where now P of x is a statement that depends on x. Now this means that for all x is in A implies P of x. Now, our book omits the parentheses. So just a note for our textbook. So Bellarmine just simply writes, for all x in A, P of x. I'm going to continue to just put a parenthesis in here. But then just keep be mindful that this here is what this is. And here's an illustration of that being used, where our P of x is now the statement x is a even integer or an odd integer. And in doing it in this manner, we omit having to write that implication, which we had initially. We have for all x, x is an integer implies that x is even or odd. Whereas now we are simply saying, for every integer x, x is even or x is odd. Similarly, if we talk about existence, the existential quantifier, we can do the same situation. We now have that there exists x in A, P of x. Now, this is not going to be an implication, but what this means is that there exists some x such that x is in A and P of x holds. And so we can write this as x is in A and P of x. And so now we have our way of writing existence with a statement that depends on x in shorthand and then in long form. But what if we wanted to negate statements that had a for all or there exists? So for example, let's look at the definition for subset. We have that A is a subset of B, means, as we saw last time, that for all x, x is in A implies x is in B. Just to tie this in with what we just discussed, we can also write this as for all x in A, x is in B. And so now this is the abbreviated form. But what if we wanted to negate the statement? That is, what if we wanted to say A is not a subset of B? What does that mean? Well, let's analyze this with a Venn diagram. If we had our set A, so here's A. Now, if this is not contained in B, that means that there must be some portion of A that does not lie entirely within B. And so, for example, we can have B be the following circle here. And so we see that there is some portion here that is not contained within B. And so if we were to translate this into symbols, this is telling us that there is some element within A itself that does not lie in B. And so we now have that here, we will have that there exists some x in A such that x is not in B. But now notice that this is the shorthand notation that we just introduced, because we are saying now that there exists x in A, x not in B. But if we look back at our shorthand notation, we want to interpret this as x is in A and P of x, where now we have this statement here, and so now we can rewrite this. This is the same. This was the shorthand, so now we were to write a long form. We can write this as there exists x is in A, and x is not in B. And notice that this is exactly what we are getting at, because we are saying that there is some element that is in A, but it's not in B. So next, we want to go ahead and negate this statement to get back what we said over here. So now, we will negate A is a subset of B to get A is not a subset of B. to do so, we use the quantifier negation laws. And what the quantifier negation laws tells us is that if we have not, there exists p of x, that is equivalent to, for all x, not p of x. Similarly, if we do not, for all x, p of x, then that is equivalent to there exists x, not p of x. So let's see that in practice. So we are going to be negating our statement for A is a subset of B, and so we have that A is not a subset of B, and here I'm abusing notation, and so since we define A is not a subset of B, and we saw this symbolically, this is what that would be, and so what we want to say, actually I'm not going to use notation. So let's start off like this. So we have not A is a subset of B. So now this is logically equivalent to not for all x, x is in A, implies x is in B. But let us recall that if we have P implies Q, that this is equivalent logically to not P or Q. And so with that in mind, we can go ahead and rewrite this as not for all x, and the not P of x, which is now the implication, the x is in A, implies x is in B. The not for all is there exists x, and to negate the implication, we're going to switch this over to not P or Q. And so not P becomes x is not in A, or x is in B. Now we distribute the negation. And so in other words, we're applying De Morgan's law. So when I say distribute the negation, I really mean De Morgan's law. And so now we're going to have x is in A and x is not in B. And so here we use De Morgan. But notice that that's exactly what we had from our consideration of what it meant to be A is not a subset of B. And so we do have that this here is in fact, symbolically, A is not a subset of B. And so we got our desired statement. And so now this is an illustration of how we use the quantifier negation law in this. So let us do another example. We are going to go ahead and negate the following statement, A intersect B, where now A and B are sets, is not equal to the empty set. And so we want to first write that in terms of its logical form, and then negate it, and find an equivalent form where the negation symbol does not occur. And so that's what our book refers to as a positive statement. It's a statement, a logical statement that has no negations occurring in it. So how do we go about this? We have A intersect B is not equal to the empty set. Well, what does that mean? Well, we know that if this is not equal to the empty set, that means that by definition, there is some x in A and some x in B. So by definition, A intersect B is the collection of x's such that x is in A and x is in B. So consequently, A intersect B is non-empty, is asserting the existence of some element in this set. And so this means that there exists some x where now x is in A and x is in B. And so we have this here. So if we wanted to negate this, so I'm just going to go ahead and just write it like this. Now this here will be the same as negating the statement here. But now keep in mind the quantifier negation law in this situation. So we have that not there exists x, p of x, is the same as for all x, not p of x. And so by the quantifier negation law, we get that this here becomes, well, let me not skip a step and just copy this over here. And so just recopying it. And so now this here will be logically equivalent to for all x, and then not p of x, where now the not p of x is now going to be x is in A and x is in B. And so now here we're using quantifier negation. Quantifier negation law. I apologize for my handwriting there at the end. And so now we can go ahead, apply the Morgans once more. And so we have the statement for all x is not in A, or x is not in B. But now what this is telling us is that we never have an element that is in both A and B simultaneously. And so this is the same as A intersect B is equal to the empty set. And so the key idea here is that we are starting with A intersect B is not the empty set. By negating, we are getting what we naturally expect. The negation of this would be that the intersection of A and B is the empty set. And that's what we actually do have, is that now this statement is telling us that for every x, we have that x is not in A, or x is not in B, which we read more apparently from the negation symbol over here, but we know that these are logically equivalent by the Morgan's law. So let's do one more example using the quantifier negation laws. In this situation, we're going to have now a statement that has both quantifiers, and as we saw in our last lesson, the order of the quantifiers is important. And so here we have there exists x such that for each y, we have that y greater than x implies the existence of some z such that z squared plus 5z is equal to y. And so here the universe of discourse is taken to be the real numbers. So we want to go ahead and negate this statement and write it in an equivalent positive way. And so let's go ahead and do that. So if we negate this, and so I'm just going to go ahead, copy it again. So when we negate this expression, this is going to be logically equivalent to, by the quantifier negation law, we're going to have not there exists, so that's going to be for all x. But now the p of x is now going to be, that statement is going to be the whole statement over here. And so we're negating this whole expression. So this here will be logically equivalent, so for all x, and then we have not for all y, and then the rest of the statement, which I'm just going to go ahead and put in parentheses here. And so this here is just this expression again. And so now here we use, once again, quantifier negation law. So this here is logically equivalent to, for all x, we apply the quantifier negation law once more, and then that not for all y becomes there exists y. And now we have not of everything into parentheses. But in order to proceed, we have an implication symbol. So we have P implies Q. So we want to write this as not P not P or Q. So we're going to negate this. The negation of y is greater than x is y is less than or equal to x. And so we have y is less than or equal to x, or Q, there exists z, such that z squared plus 5z is equal to y. So we go ahead, now we apply De Morgan's law inside, and so now this becomes logically equivalent to, and so let me just write this again, it's quantifier negation law here was used again. And I forgot the conditional law. So here we did two steps in one. We did the quantifier negation law, but we also switched the P implies Q to not P or Q. So let us continue. So now this is logic equivalent. We're going to apply De Morgan's law. And so applying De Morgan's law forces us to now negate this once more, and so we're back to y is greater than x. And a not there exists z. And so what I'm going to do now is write this as for all z. Since we're going to have a not there exists z by De Morgan's law, and then we're going to have not z squared plus 5z equals y. And so here we did De Morgan, and we once more use the quantifier negation law. And so finally, we now have for all x, there exists a y is greater than x, and for all z, if we negate the expression z squared plus 5z is equal to y, then we have a not equal. And so we have z squared plus 5z does not equal y. And we're done. We have our desired expression. So next I want to discuss just some notation from our book. So our author uses this notation here. There exists with an exclamation point x. This means there exists exactly 1x. So next I'm going to make a definition. So let A and B be sets. We say that A is a proper subset of B, which we're going to denote by A subset symbol. So denoted by A subset B, or A is a proper subset of B, if A is a subset of B and A does not equal B. The terminology proper subset, that is a standard term in mathematics. However, depending on which book you're using, the notation does vary. So for example, so I'm going to write this as a warning for the future. So some authors write, actually I'll say most authors write, A is this notation here to mean A is a subset of B. These authors will distinguish the situation of A being a proper subset of B by writing a subset, but now this notation right here. And so now this is indicating to the reader that A is a subset of B, but it is not equal to. And so this is the actual notation that is mostly used throughout mathematics. But our book does make things differently in the sense that we're using this subset notation with the underline right below it. And so whenever we use this for our course, we mean subset, but if we use this notation, we mean proper. And so when in your future math courses, something to be on the lookout for is, what does this notation mean? Because if you take it to be proper and the author means subset, there will be some confusion down the road. And so that's something you want to be mindful of. Similar to our discussion of the natural numbers. In our course, the natural numbers include 0. In number theory, the natural numbers do not include 0. And so it's one of those notations that changes from course to course. But again, the terminology of proper subset, that is standard. Namely, A is a subset of B, and A is not equal to B. So let us return to sets. So here we have a collection of sets, X, A, B, C, D, E. And so X is the set of elements containing 1, 2, 3, 4, 5. A has 1, 2, 3. B is 3, 4, 5. C is A union B. D is A intersect B. And E is going to be the set difference of X minus A. So pause the video and work out what C, D, and E are. So here we have it. If we take A union B, we will have that since A has 1, 2, 3, B has 3, 4, 5, the union of the two, by definition, is going to be those elements in A or B. And so we're going to have 1, 2, 3, and 3, 4, 5 all together. However, in a set, if we double count, so we have 3 appearing twice, we really are only counting that element once. And so we really do have the set 1, 2, 3, 4, 5. Similarly, if we take A intersect B, the only element that A and B share in common is 3. And so now this is the set containing 3. So not the element 3, since 3 will be an element. We want to talk about a set. And so now we have the set containing 3, and similarly, the set difference of X minus A is the set containing 4 and 5. And so we have this here. So now let us ask the following question. So how many subsets does D have? Well, we always have that, we know that A, actually let me use this, since we already have the symbol A being used, let me go ahead and use the symbol Z. So we know that for each set Z, we have that Z is a subset of itself, and the empty set is always a subset of Z. Thus, we have that in the case of D, we have that the empty set and itself are subsets of D, since we just have the set containing 3 elements. So D has exactly 2 subsets. What if we were to look at E? If we were to look at E, now we have the set containing 4 and 5. So we still have the empty set and the set the whole set itself, 4 and 5. But we now have that 4, the set containing 4, is a subset. And we also have that the set containing 5 is a subset. And so these are all subsets of E. And these are all the possibilities. We've exhausted all the possible combinations we can have. And so E has exactly 4 subsets. So what I want you to do next is to compute how many subsets A has and how many subsets, and take a guess at how many subsets X has. And more generally, if you have a finite set, how many subsets does it have based on the number of elements in it? So based on the patterns that we are looking at, make a guess as to what that value is. So more precisely, we have the following question. So here's the question. So let's go ahead and take n to be a natural number, a to be a set with n elements. I want you to make a conjecture on the number of subsets that this arbitrary set A has. So notice that now this A is now some arbitrary set with n elements. So based on your computation for how many subsets 1, 2, 3 has, and your guess for X, make a general statement about how many subsets are there in a finite set. So pause the video, work it out, and when you unpause, I'll have the answers to both. So what we end up getting is that the set containing 1, 2, 3 has exactly 8 subsets. Namely, the empty set. We have 3 different subsets that each have exactly 1 element. We have 3 more subsets that each having 2 elements, and finally the whole set itself. And so we have that there are exactly 8 subsets of the set 1, 2, 3. Now if we put everything together, we have that there are 8 subsets in the set 1, 2, 3. In the case of 4, 5, the set containing 4, 5, we saw that there are 4 subsets. When we look at the case of a set containing 1 element, namely the set containing 3, we have 2 subsets, the empty set and the set containing 3. So this leads us to ask the following conjecture. Is the following true? If A is a finite set with n elements, here n is a natural number, then our computations seem to imply that A has exactly 2 to the n subsets. Now, we're saying now something about every natural number based on only 3 examples. If n is a natural number, we also have to ask, well, what happens if n is equal to 0? What happens then? Well, if we do the n equals to 0 case, we can take the empty set. Well, in the case of n equals to 0, the only set with 0 elements is the empty set. And so we have that the empty set is a subset of itself. So the empty set has exactly 1 subset. And so it matches up, because if we plug in n equals to 0 here, we have 2 to the 0, 1. And so this works out. Now, what we want to do next is consider the set containing the subsets that we were just looking at. So what if we were to look at all these subsets and make a set containing the subsets of 1, 2, 3? So all we're doing now is putting in some brackets here, and so now we have a set. This has 8 elements. So this is a set a set consisting of 8 elements. Now, at first glance, we see that this is a set whose elements themselves are sets, and so we have more structure here than just the original set where we just had 1, 2, 3 as elements. So I want to clarify something when it comes to sets. We're viewing the empty set now as one element. We're viewing the set containing 1 as another element. The set containing 1, 2, and 3, that's also one element in this larger set. And so when we count these off, we have 8 elements. Since each of these sets that we have inside, they are not equal. And so we have 8 distinct elements. Hence, our set being finite with 8 elements. Now, to clarify that, let's think about this idea here in the following way. If we look at H is the set of all colleges. Now, Carlton is an element of H. If we look at the set containing Carlton, well, this is a subset of H. But when we're looking at this as an element of H, we are ignoring the additional structure that Carlton has. Because when we say Carlton, it's more than just a word. We can talk about all of us. So students, faculty, staff, we are all part of Carlton. We also have the buildings that Carlton has. And so as an element, we can view Carlton also as a set of various different objects. But when we view it in this way, this is a set containing one element, namely Carlton. We are ignoring the additional structure that Carlton has. In the same manner, when we say that this has 8 elements, we are ignoring the additional structure that each of these sets within the set that we have here. So for example, as another illustration of this, if we were to take the set which has the real numbers inside, this has 1 element. Yet the real numbers is an infinite set. But now we're ignoring that additional structure in this situation. And so that's something I just want you to be mindful of in terms of how we use this language, is that when we're talking about sets of sets, we do ignore the additional structure that those sets themselves have. So let's formalize our discussion. So what we have been looking at is actually what is known as the power set of a set A. So the power set of A, which we denote by script P of A, is the set whose elements are all subsets of A. And so the power set of A symbolically can be written as the set consisting of those x's such that x is a subset of A. And so here's where, at a first glance, this notation can be a bit confusing because we're used to thinking about lowercase x as an element. But now we're thinking this x, lowercase x, is actually a subset. And the examples that we just did are all examples of power sets. Well, the examples before we were talking about the set containing Carlton. And so we look at the power set of the empty set, that's the set containing the empty set. The power set of the set 3 is the set containing the empty set and the set 3. So on and so forth. And so now this set has 1 element, this set has 2 elements, this set has 4 elements, and lastly, this one has 8 elements. And so now we have an illustration of where a set is constructed so that its elements are sets. And such sets we call families. And so we say that F is a family of sets if F is a set whose elements are themselves sets. And so all the examples that we just looked at in terms of the power set of the empty set, power set of the set containing 3, these are all examples of families of sets. And if we have a family of sets, we can look at the intersection and union respectively of the family. And so we have the intersection of F and union of F. And so before we look at the more general setup, let's interpret what this notation means for union and intersection. So let's start off with the nicest possible case. So let's go ahead and take F to be a set containing two elements. And so let F, actually, so first off, let A and B be sets. And let F be the set consisting of A and B. So when we're looking at the intersection of F, we're looking for those elements X such that we have for every and so now we have, but now notice that because we're working with a explicit example, namely the set containing A comma B, we want to have that X is in A and it is in B. And so I'm going to change the symbol since I used A over here and we have the A here. So I'm going to change the notation. So here is X such that for all C, we have that if C is in F, then this implies that X is in C. So what does this mean? Well, we only have two possibilities for what this C could be, namely A or B. And what we want to say is that since we have the for all, if we have our set A and B in F, then X has to be in A and B. So in other words, we really are looking at the intersection of A and B, since this will be the set consisting of those X's such that X is in A and X is in B. Except that now we are rewriting this. So that is those X's, and we are replacing this X's in A and X's in B by extracting the sets themselves, putting them on the outside with a quantifier for all C, where C is in F, implies that those elements are in C. In a similar manner, you can verify that if we look at the union of F's, that this is the union of A and B. And so I leave it to you to verify that this here is what we end up getting in this example. But now, let's do a concrete example with some actual sets that we can work with. So let's look at the set where now we have 1, 2, 3. And then we have 1, 2. And we have 3, 4, 5. If we take the intersection of these F's, of the family, by definition, what this is going to be is going to be the intersection of each of these three together. We're looking at the collection of elements that are all simultaneously in each of these sets. So in other words, the intersection of 1, 2, 3 with 1, 2, intersection of 3, 4, 5. And this here, the only element that they all share in common, oh, I meant to have put a 3 in here instead of a 2, but now because I did not, this here is going to be empty. Because 1, 2, and 3, the intersection with 1 and 2, this is going to intersect to just be the set consisting of 1, 2. But then when we look at the set of 1, 2 with 3, 4, 5, they share no common elements. So this will be empty. When we look at the union of F, now we are going to get back the set 1, 2, 3, 4, 5. And so we're choosing our union is going to have an element in each of these sets. Now, the notation that our book uses for family and the union and intersection is not commonly used, but rather we use the index notation. And so in this notation, we still have our family of sets, but now we're going to be writing it in the following way. We have f is equal to a sub I, where I is in some capital I, and here we call I an indexing set. So before we continue with this terminology, I want to come back to the example we just did. So we were just looking at in the previous example at this collection of sets. So I'm going to go ahead and copy this. And so let's talk about what it means to index and tie in this with the notation with the a sub i's. So what we are going to do now is call each of these. So the set 1, 2, 3, we're going to denote by a sub 1. The set 1, 2 is going to be a sub 2. And the set 3, 4, 5 is going to be a sub 3. And so we can take our index set to be the set 1, 2, 3. And so now f can be written as the set of a sub i's such that I is an I. But the idea behind indexing is that we don't necessarily have to index by numbers, but we can index with any set. And what I mean by that is we could have instead done this in the following way. So instead of using numbers to index, what if we use emotions? So a smiley face, a sad face, and a let's say that that's angry. And so our index set now is just the set containing those symbols. So smiley face, sad face, and angry or indifferent. And so we have our set I. And so we again can write f as the set, and because we already use I, I'm going to change this to a j. And so now we can write this as this f as the set consisting of those a sub j's. J is in j. And so that's the idea behind an indexing set. It doesn't necessarily have to be composed of numbers, but you can index over any set. So here I chose these 3 emotions. We could have indexed over chairs or the real numbers. And so that's the idea. So this lends itself to be done in more generality. And so with that in mind, when we use this notation, the union of f can be written instead as the intersection of the a sub i's, where I ranges through the indexing set. So this is in English, we read this as the intersection of the a sub i's as I ranges over the indexing set I. And this is something to be mindful of when writing things down versus reading them out loud. When I read this out loud, there is an ambiguity as to what do I mean by I. Do I mean the lowercase or the set itself? We can easily bypass that when writing things down to percent by switching this I to a J. And then we could have J is an I, J is an I, and X is an A sub J. And so that's one way that we can remedy the ambiguity of what does I represent, lowercase or just indexing set. And so we do have now this notation. for unions and intersections. To finish off our lesson for today, let us consider the following example. So I'm going to go ahead and take our indexing set to be the positive integers, and we're going to let our a sub j be the interval -1 over j, comma 1 over j. And I'm using the notation from calculus. Oh, and I forgot, j is a positive integer. And so the notation in calculus that we use for this is that this is the collection of real numbers such that -1 over j is less than, strictly less than, x, which is strictly less than 1 over j. So what is the intersection of those j's and I such that, and a sub j here, and also the union? Now, a common notation that is used, we're looking at the intersection as j ranges over I, which is the positive integers. And so oftentimes we simply can write in this case j is equal to 1 to infinity. And so this matches up with our notation that we learn in calculus for infinite series. And so we can say the union from j equals 1 to infinity of these a sub j's. So now, in the case of the union, this is going to be the interval -1, 1. Because if we think about the number line, so here is our number line, and so the set a sub 1 is going to correspond to -1, 1. So we're looking at the open interval -1, 1. But then when we plug in j is equal to 2, we're going to have -1/2. Actually, let me change the color. And then over here, we're going to have 1/2 over here. And so this will be a sub 2. And this is just to get us to bring intuition. So I'm not being rigorous in the sense that we're not doing any element chase yet. And so we'll do that afterwards in our next lesson, and more discussion on that. But this is just to get some intuition for how this relates to notions that we have discussed previously. And so we have our a sub 2, -1/2, 1/2. And then so on and so forth. We're always going to get, as we progress through the positive integers, the -1 over j's and 1 over j's get smaller in absolute value. And so what we're going to have is this descending chain of smaller open intervals. And so when we take the union, it's just going to be the whole collection -1, 1. But with the intersection, I want you to convince yourself that this is the set containing only 0. And so we're going to continue our discussion of sets, but in our next lesson we are going to move towards a discussion of proof methods.